Does this system of equations have a solution? What is the area of this coordinate triangle? Does this matrix have an inverse? And if so, what is it? The answer to all of these questions may not seem related, but they actually are. And they can all be summed up by one number, a number called the determinant. And that's what our video is about today. Consider the following 2x2 system of linear equations. X plus 3y equals 2, 2x plus y equals 3. Does this system of equations have a solution? What does it mean for a system like this to have a solution, or to not have a solution? There are really three possible outcomes when two lines are graphed together. The two lines can intersect at a unique point. The two lines might be parallel, in which they will never cross. Or the second equation is really the first equation in disguise. In other words, they're describing the same line. We'll focus on equations that have a unique solution, and our determinant will be able to tell us if that's the case. If I were to set up a matrix equation for this system of equations, it would look like this. So the numbers that I'm really concerned with are the coefficients in front of the x's and y's. When they're lined up in this way, and just taking the numbers, the coefficients, in a matrix, a rectangular array of numbers, this one is a 2x2 matrix. It has 2 rows and 2 columns. So matrix M has the row 1, 3 and a second row 2, 1. And when we find the determinant of a 2x2 matrix, we're going to be multiplying the numbers along the diagonals. So along the main diagonal, A times D, minus along the other diagonal, B times C. So in our matrix, if we take 1 times 1 minus 3 times 2, we get the determinant to be equal to -5. So since it is not equal to 0, this means our system has a solution. A solution exists. But now we must find out what that solution is. And the determinant is going to play a role in finding that solution. There are many methods for solving a system of equations. Here, let's first look at graphing the two lines. When we graph them, we see that they do in fact have a unique point of intersection. So we're going to use our matrix inverse to find that unique point of intersection. Setting up our matrix equation, we're going to have to multiply the right-hand side by the matrix inverse. So first we calculate the determinant, because this is going to be part of finding the matrix inverse. And there is a formula for finding the matrix inverse. Here, that matrix inverse formula is going to be given in the following way. And we use m to the -1 power to denote the inverse of the matrix. It is equal to the matrix cofactor transpose divided by the determinant of the matrix, which all sounds very fancy. So we know what our determinant is, it's -5. And the other thing we have to find is this thing called the cofactor transpose. So given a 2x2 matrix, if you switch the elements along the main diagonal and negate the other elements in the matrix, you've found the cofactor transpose. So applying that idea to our matrix, 1, 3, 2, 1, switching the main diagonal and negating the other two, and then multiplying or dividing by -5 is the same thing as multiplying by -1/5, we get our matrix inverse. and the entries are fractions, which is often the case with finding an inverse. Now, doing a little matrix multiplication of our inverse multiplied by the right-hand side of our equation 2, 3 yields the result 7/5 and 1/5. These are our x and our y values. In other words, this is our unique point, our unique solution, our unique point of intersection. So this is the answer to the system of equations, and like I said, there's other ways that we could find that answer. This one is using matrices. Now, how do you find the area of this coordinate triangle? You might remember what the area formula for a triangle is. Right? It's area equals 1/2 its base times its height, where its base and its height are perpendicular to each other. In this picture, though, it's kind of hard to see the base or what the height is that's perpendicular to the base. So one method we might approach to get the area of this triangle in algebra would be to encase this triangle in a rectangle. And this rectangle, by looking at the graph, is a 6x4 rectangle, which gives it an area of 24. Now, if we look on the grid, the parts that we don't want in that rectangle are really 3 right triangles, and a right triangle always has its base and height perpendicular to each other. So their areas will be easy to find. So noting the length and width, or the base and the height of each of those right triangles on our grid, we can find the area of each of those right triangles separately. So the first one has an area of 2, the second one an area of 15/2, and the third one has an area of 3. So adding those 3 areas up will give us the area of those 2 triangles. And if we subtract that area away from our rectangle, we will have left over the area of the triangle we were interested in, highlighted in yellow on our grid. And so by 24, the area of the rectangle, minus the area of the purple right triangles, we get a total area of our rectangle to be 23 halves. Or, if you like decimal approximations, this is not an approximation, it's exact 11.5. 11.5 is the area of that triangle. So what does this have to do with the determinant, right? We didn't use the determinant here in any way so far. Well, we can. And so there's a formula relating the area of this triangle and its coordinates of its vertices to the determinant that we can make with these vertices. So if we take the coordinates A, B, and C of the vertices of this triangle, and we're going to create a 3x3 matrix with these numbers, so we're going to add a few coordinates to it. We're going to add a third coordinate to these ordered pairs, making them ordered triples. We're going to make the third number in each of those 1. Now, aligning them so that they form a rectangular array or a matrix, we get 1, 1, 1, 2, 5, 1, 7, 2, 1 as our matrix. Now, the area of our triangle is going to be equal to plus or minus 1/2 the determinant of this matrix. And it's plus or minus 1/2 because area always has to come out positive, and sometimes the determinant gives us a negative number. So when we calculate a 3x3 determinant, we copy the first 2 columns to the right side of that matrix so that we can look at diagonals along one way and then diagonals along another way. So we're going to be multiplying numbers along diagonals, and when I go from left to right going down, I give a positive product. When I go from right to left on the diagonals, highlighted in green, I'm going to give those negative values and then add up all the results of those products. That's going to give us the determinant. So we here get a determinant of negative 23, and putting this into the formula for the area of a triangle, it's negative 1/2 times the negative 23, so we get a positive area of 11.5. So we verified our result in 2 ways, one way with our determinant, and another way using a bit of geometry and coordinate geometry. The beauty of mathematics is that there is usually more than one way to solve a problem, and sometimes these other ways are not as obvious, but they are related to each other and equivalent. Next, let's find the equation of the parabola shown here, where 3 of the coordinate points on this particular parabola are given. So we have 3 points, 3 values of x and y that satisfy our quadratic equation, which in general is given by the formula y equals ax squared plus bx plus c, where a, b, and c are just real numbers. And that's actually the goal of our problem, is to find those coefficients, those real numbers, so that we know what the exact equation of this parabola will be. So using the coordinates, which are x and y values, we can substitute one at a time into this formula and get 3 quadratic equations in terms of a, b, and c. So check this out. If we take the quadratic equation formula and plug in the first point p, which is 1, 1, x is 1, y is 1. All right, substituting those in there will generate our first equation, a plus b plus c equals 1. Next, we're going to take q, which is 2, 2, and do the same thing, and that's going to generate a second equation for us here, 4a plus 2b plus c equals 2. And our third point will generate a third equation for us, so now we'll have the equation 9a plus 3b plus 1c equals 7. And these 3 equations in these 3 unknowns, a, b, and c, constitute a system of equations, a 3x3 system of equations. And we're going to solve this system of equations using something called Cramer's rule, which also uses the determinant. But we're going to find 4 different determinants. So we're going to take the original matrix M, find its 3x3 determinant, again by copying the first 2 columns and then looking at the diagonals along from left to right and then from right to left. The ones from right to left are getting negative signs when we find the products along those diagonals. And then we add up the results, that's our determinant. So we do this for the original matrix M, and we record that, we'll say that that's determinant D, and we'll call that -2 because that was the number we got. Next, we're going to take that matrix M and we're going to replace the first column in it with the matrix C, which is on the right-hand side in blue, the numbers 1, 2, and 7. All right, and we're going to call this determinant matrix sub x, or just determinant x. All right, so determinant sub x is going to be found by doing the determinant of this matrix with that column replaced. So I like I did before, copy the first 2 columns on the right-hand side of the matrix and do my little diagonal dance of multiplying the numbers along the diagonals from left to right. The ones from right to left get the negative signs, and we add up all those numbers, and we get a new determinant. Here, d sub x is -4. Now I'm going to repeat this process for the other 2 columns, taking now the second column and replacing it with the numbers 1, 2, 7, the matrix that's on the right-hand side of our equation. We'll call this determinant matrix determinant sub y, and when we do this, again copying the first 2 columns on the right-hand side of the matrix and doing our little diagonal dance, we multiply the numbers along the diagonals, and then from right to left those get negative signs as we multiply them, and then we add up all the numbers together. Our determinant d sub y works out to be the number 10. So we have one more to do where we replace the third column of matrix M, and then we're going to call this determinant d sub z, or d sub z, depending on where you come from. So here, again, replacing the third column with 1, 2, 7, copying the first 2 columns and doing our diagonal dance for the determinant. Here, we get a determinant that works out to be, let's see, -8. All right, so now we have these 4 numbers, and now we can start putting together Cramer's rule, which is going to give us a solution to our system of equations. So normally, in a system of equations, instead of ABC, we'd have x, y, z. So we're going to treat those as the same thing here. X, y, z, or ABC, would be found by doing the determinant sub x over the regular or original determinant. And then for y, d sub y over the original determinant. And for z, d sub z over the original determinant. So you'll see when we use these numbers in ratios, and those are going to give us our a, b, c values. In our equation, those are the coefficients of our parabola. So we've used a determinant in this thing called Cramer's rule for a 3x3 system, which could be used to any square system, and it'll give you a solution as long as the determinant exists. The determinant has to exist. It cannot be 0, because you can see we'd be dividing by 0 in that case. So next up is, what is the geometric interpretation of this determinant. We've been using it to solve equations, but what does it mean? And we can best understand this in the realm of vectors. So here on the left-hand side, I'm building two unit vectors, vectors of length 1 along the x and y axis. And these are just arrows pointing from the center to the points 1, 0, and 0, 1. And if I look at the area that the length and width of those vectors create, it's an area of 1. Now, let's say we have some matrix M, which is a linear transformation. It's just going to change these vectors in a new way. So what we do is we filter these two basis vectors through the matrix to see what they do to the matrices, the vectors, how they change them. So, for instance, if I take the matrix 1, 0 and put it through this matrix, I get the new vector 3, 0. And if I take the vector 0, 1 and put it through this matrix, I get the new vector 1, 2. And if I look at the form of the geometry that comes with those vectors, the area that is spanned by those vectors is a parallelogram. And if I calculate that, I find the area of that to be 6, which also happens to be the determinant of the matrix M. So we see that the determinant is actually something that tells us how much area will be scaled up under a linear transformation. And this has some really deep ramifications in higher mathematics, especially in linear algebra. So again, we took an area of a box that had an area of 1, and it got scaled up or multiplied by 6 to have now an area of 6 under the transformation. That means all vectors in the plane got scaled up by a factor of 6 in the area. And so you can really look at what the determinant does through the eyes of vectors. Speaking of vectors, the determinant can tell us something about vectors in 3 dimensions as well. So let's say we have two vectors that live along the x and y axis in 3 dimensions. So we have 3 coordinates in our vectors. The vectors u and v are 6, 0, 0 and 0, 8, 0. And we're going to find something called the cross product of these two vectors. This cross product is defined by a determinant. The determinant of the basis vectors I, j, and k defined above, and our two vectors u and v. Now, just like we did before, finding the 3 by 3 determinant of this determinant vector matrix, we're going to go along the diagonals, multiply what we have along the diagonals, and add up the results. The diagonals going from right to left get the negatives, but in this case all of those are 0. So the result of taking these two vectors along the x and y axis gives us a vector that lives directly along the z-axis. We'll call that vector w, and it has a length of 48 here. So we see that a transformation of a rotation of vectors by 90 degrees, mutually perpendicular to both of those vectors, is what we got here. Essentially, we got a vector that is perpendicular to the plane in which the vectors u and v live on. A transformation that was a rotation in 3 dimensions. Exploring vectors in 3 dimensions, along with linear transformations, has paved the way for subjects such as differential geometry, which applies calculus to higher levels of geometry, using things like manifolds and normal vectors, and this thing called the Gauss map. Hey, thanks for watching, and please hit that like, subscribe, and notification bell for more videos. Stay tuned.